Okay, so welcome to this Asiagraphics webinar session 5. So this is the Peng Song from Singapore University of Technology and Design. So in this session, it's my great pleasure to have 3 speakers, Shiwen Fu, and Xianzhi Li, and Ray Li. They will give research topic on machine learning for point cloud processing. So our first speaker is Shiwen Fu. He will give a talk on deep 3D sensing pipeline, feature learning, pre-processing, understanding, and applications. Shiwen Fu is currently a full professor at the Chinese University of Hong Kong. He served as the associate editor of IEEE Computer Graphics and Applications and Computer Graphics Forum, co-chair of SIGGRAPH Asia 2016 Technical Brief and Post Program, and a member in SIGGRAPH 2019 Doctoral Consortium and Program Committee members in various research conferences, including SIGGRAPH Asia Technical Brief, SIGGRAPH Asia Emerging Technology, IEEE Visualization, AAAI, CVPR, IEEE VR, VRST, Pacific Graphics, GMP, and so on. His recent research interests include point cloud processing, 3D vision, computational fabrication, user interaction, and data visualization. So, hi, Professor Fu. So now the floor is yours.
Yeah, thank you, Song Park. Maybe let me share the screen first.
Yes. So let me start sharing.
Okay, can you see my screen?
Yes, I can see.
It seems the screen is still not broadcast yet. Is it?
Really?
Oh, okay, you got it.
Yeah, so the floor is yours.
Okay, thank you, Song Park, for the introduction, and welcome everyone for attending my talk. Okay, in today's talk, I will focus on the 3D sensing pipeline, which starts from feature learnings and ends with some downstream applications. And in fact, the 3 talks today are deeply connected. In my talk, I will focus on overviewing my research works on different parts of the 3D sensing pipeline. So in my part, I will mainly introduce the key ideas and our major results and skip the technical detail. Then in the next 2 talks by Professor Li Xianzhi and also Dr. Ray Li, they will give a deep dive into the technical details of their work in the 3D sensing pipeline. Okay, so let's get started. When we start a research project, we must start with a clear research goal. So what is the goal of the 3D sensing pipeline? Having said that, I mean that after we use various kinds of sensors to acquire data about our physical environment, no matter the environment is indoor or outdoor, in object level or in human level, what we may achieve, okay, with the acquired data is the key issues. Okay, essentially the end goal of 3D sensing is to extract certain 3D information or 3D structure out of our acquired data from the sensors, such that this high-level information can provide a 3D perception of the space so that we can further support or enrich various kinds of relevant downstream applications. Here, I show you some of the applications that my group has done, which includes real-time 3D object detections, 3D scene understanding, and recently, we also work on some projects with mechanical engineering researchers, and our goal is to enable the robots to have a 3D perception of the environments such that we can effectively pick small objects in a bin. Also, by sensing our hands and reconstructing screen-aligned 3D hand measures in real time, we can also support various lawful user interaction scenarios, particularly as so in this work. Our method, okay, our real-time method is able to enable the user to directly use bare hand to grab and manipulate virtual objects in AR environments, so that the phone you see here are actually virtual, but the hand here is actually real. Now, let me show you the 3D sensing pipeline. After we acquire the data from the 3D space, I think the very first step is feature learning. It is because most of the 3D sensing and 3D perception methods nowadays are based on deep neural networks. Then we need to preprocess the data, for example, to denoise the data, to upsample the data, or to consolidate the data. After that, we can try to process the data and extract high-level 3D structure or 3D information out of the data. For example, for the purpose of object localization and object segmentations to support, and then based on these kind of high-level information, we are able to support or enrich a wide variety of downstream applications. So let's look at each of these 4 components in the pipeline one by one. The first one is feature learning. For feature learning, I will share with you the following 3 research works, which is published in the recent 2 to 3 years. Nowadays, we all know that the quality of features are very important for promoting the performance of many methods, especially most methods nowadays are based on deep neural network. Following PointNet, an early work that we did is PointWeb, in which we try to enrich or enhance the point features by densely connecting each point with every single label in a local neighborhood, such that we can promote the message passing or information exchange between points in local neighborhoods. And then the network can thus be able to learn to have better feature representation for the local neighborhood. In PointWeb, we also developed several lawful modules to enhance the point features interactions and demonstrate the capability of our method on improving the performance of various tasks, such as point clouds, 3D segmentation, and also 3D object classification. For detail, please look at our paper. Another aspect that we have tried for enhancing the point feature learning relates to the data augmentation. Unlike existing data augmentation techniques, which are often based on manual design or based on some heuristics, we design point augment. It is the first approach that explores how we may automatically learn to augment point cloud samples to enrich the data samples, diversity of the data sample. Okay, essentially, point augment is an automatic augmentation framework in which we adopt adversary learning to jointly optimize an augmented network, okay, which is the one I showed here. And then on the other hand, we also have another network, which is the task networks. And particularly in our method, we actually take the feedback or the loss values from the task network to train and improve the augmented network such that it can learn to augment and produce point cloud samples that better fits the task. Okay, and then in this point augmentation function, I want to highlight that this function is learnable with a strip level transformation and also a point level displacement for highly robustness. Lastly, we also demonstrate that by using our method, we can incorporate our point augment into different kinds of classification networks, and then we can show that by doing so, we can improve the model performance of many methods. Again, for more details, you can refer to the paper. Lastly, we explore rotation invariant point features. The motivation behind this work is that most existing works simply take 3D point cloud as input for extracting point features from the point clouds. Hence, they have good performance mainly when the test objects have the same or similar orientation as the objects in the training set, which corresponding to the blue bars here in the blue bar here in the plots. Because for the both blue bar, it means that we train on the C axis and then test on also the C orientations. In other words, when we try to use this kind of trained networks on different kinds of for objects with different kinds of arbitrary orientation, they will have more poor generalization, which corresponding to the orange bars here, which means that we train on the C-axis orientation and then try to test the trained network on objects of arbitrary orientation. Okay, to overcome this issue, we design a lawful representation shown on the right-hand side, which is purely rotation invariant, and our representation encodes not only local structure, local shape, local information, but also global information, as well as we design the representation to be more robust to noise as well as outliers. As this work will be presented in the second talk by Sanji Lee, please stay tuned and find more detail in the second talk. Okay, let's go back to the pipeline. After we extracted the point features, okay, to improve the performance and also the robustness of the overall 3D sensing pipeline or the 3D perception tasks or application in the end, another step that we often need is to pre-process the data. And in this pre-processing part, due to the amount of time I have, I will mainly focus on briefly introducing my works on point cloud upsampling and also point cloud consolidation. So let's start with point cloud upsampling, for which my group has developed a series of works on it. Briefly speaking, the goal of point cloud upsampling is that given a sparse and noisy input point cloud, we aim to produce a dense and clean output point cloud that describes the same underlying object surface. The general approach for point cloud upsampling with deep neural network is that after we extract the features for each point in the point cloud, input point cloud, then we will expand the amount of features, which means we produce more point features in the same feature space, so that we can later reconstruct one point coordinate from each expanded point features and then produce more points in the 3D object space. Okay, so in the first work we did, which is the PULETS, it is the first deep neural network model that we try to upsampling 3D point cloud. Compared with the recent work on 3D point cloud upsampling nowadays, of course, the idea in this work is rather simple. In this work, basically, our idea is that we first learn multi-level features per point and then adopt a multi-branch convolution units to expand the point features implicitly in the 3D in the feature space rather than in the physical 3D space, because in doing so we can expand the feature more easily, okay, than in the physical space. Particularly, we want to upsample the points in a patch level, which is easier to learn with a reconstruction loss to encourage the upsampled points to remain on the underlying surface, and also we develop another loss, which is the repulsion loss. So here, in which we try to push the points further away from one another in the final upsampled results. Overall, I think the major ideas in this work is that we have the overall framework that allows us to upsample point clouds using deep neural networks, and then the idea of expanding the point features in the feature space rather than in the physical 3D space. Okay, looking at the 3D reconstructed results. So on the right-hand side, based on PULETS, okay, on the chair corner, we can see that the PULETS actually can easily over smooth the edges in the upsampled point clouds. This result actually motivates us to further explore whether we can upsampling points at the same time considering the sharp edges and also try to respect the sharp edges on the underlying surface. Having said that, we aim to further preserve the sharp edges by trying, our idea is to try to generate more points, okay, along the sharp edges. So how this can be done? In this work, we developed something we call the EC-LET. EC means not easy, okay, it means edge consolidation. Okay, so to approach the problem, we first create a regression loss, okay, in which in this loss or regression component, in which we try to recover the 3D coordinate. And then after we recover the 3D coordinate, we try to estimate the distances between each of the 3D coordinate to the annotated edges, okay, in the resultant point clouds or in the generated point cloud. And then in the network, we try to measure this distance. If this distance is small, we try to push the points towards the edges. Okay, which means that we try to encourage the network to generate more points on the sharp edges in each patch that is being trained. So using this method, we can further formulate an edge-aware loss, John loss, to directly minimize such distances. And by this means, okay, we can further, based on the annotation, to try to push the points more close to the edges. And in doing so, we found that we are able to train the network to identify points that are near edges and also encourage these points to be closer, not just to the underlying surface, but also close to those annotated edges. In this way, our network is able to upsample more points that are closer to the edges. But of course, one deficiency in this approach is that it requires some annotation. So that's why some recent work by some other research group try to overcome this issue in a more unsupervised manner. Okay, but still you can see if you compare the result of this work, our ECLAT with PULAT, you can see the result is greatly improved. And our result is our method is able to help produce more better 3D reconstruction that can respect the edges. Also, we try to apply our ECLAT on both real scan data as well as synthetic data in order to demonstrate the capability of this work. Okay, I recall that when I was a graduate student many years ago, one of my teachers in those old days reminds us that research basically is search again. Okay, it means that we have to try to identify issues or shortcomings in the existing work and then try to overcome the issues. So that's why our third paper in this series on point cloud upsampling is this PU-GAN, which starts with the observation that the upsampling point clouds, as you can see here, okay, on the right hand side, usually have very poor point distribution pattern. Okay, so that's why we can see some of the points are actually quite close to each other. Okay, so they cannot effectively or efficiently describe or represent the underlying surface. Hence, after we finished PULAT and also ECLAT, I challenged my PhD student on whether they can design a neural networks that can produce point distributions that are more uniform, following something we call people call it the blue noise sampling pattern. Okay, after that, we actually invented the uniform laws and also the PU-GAN framework, so here, which can help us to produce much better point distribution in terms of uniformity. You may see that our results show on the right-hand side, which is more uniform than the one shown by the previous work. Okay, since the third talk today by Yuehui Li will be covering this PU-GAN, okay, I will skip the technical detail, so please stay tuned and then look at his talk later. Last year, we further revisit the point cloud upsampling task again. And our new concept observation here is that the task is in fact quite complex since it involves multiple objectives by nature. It is because when we upsampling a point cloud, we not only want the upsampled point cloud to be close to the underlying surface, we also want the upsampling point cloud to have good point good distribution, point distribution uniformity in terms of uniformity, etc., etc. Since it is quite complex, okay, to have a single network to simultaneously consider multiple objectives. So our new idea here is that we propose something we call the DPU. D means disentangle, okay, to disentangle the complex point cloud upsampling task by formulating two cascaded subnetworks, which includes a dense generator and a spatial refiner. Okay, and here you can see extensive results, okay, quantitative and quantitative results on both synthetic and real scan data demonstrate the goodness of our method over the previous work, which is a PU-GAN and so on and so forth. Sorry, PU-GAN and PULAT and so on and so forth. Again, this work will be presented in more details in the third talk today. So that's why I will skip the detail. Please stay tuned. Okay, another work that we did on 3D data preprocessing is a mesh denoising work, in which we design a deep neural network to learn to filter normal vectors on 3D meshes without requiring explicit surface information to aim a better 3D reconstruction. Due to time limit, I will skip this talk, but if you are interested in this work, you may find more technical detail in the research paper. Okay, so after we extracted the point features and also pre-processed the data, we are ready for the next step, which is 3D perception or 3D understanding or 3D scene understanding, in which we try to further infer some high-level 3D information of the environment surrounding us. And here I will introduce some works on 3D object detection, 3D semantic and instant segmentation, and also label efficient or annotation efficient 3D segmentation. And lastly, I will also introduce my very recent work on 3D to 2D distillation method for scene passing. So, okay, let's go to the first one, which is 3D object detection. In this, in the research literature, research on 3D object detection mainly focus on autonomous driving scenario, which means the goal is to detect 3D bounding boxes that enclose or locate the objects such as cars, bicycle, pedestrian in the input point cloud. To meet the sheer practical needs, the detection should not only be accurate in terms of FH precision, but also be fast in terms of the network inference speed as shown in the plot on the right-hand side. We can see that more recent work are focusing on both speed and accuracy nowadays. And if you look at the shaded area in this plot, you can also see that the shaded area actually help to mark the methods that can run in real time. And in our very first work, which is this called CIA-SSD, SSD stands for single stage object detector. Okay, we aim for both high speed and also high precision. So in this work, we first develop and also design a lightweight module, okay, to help us to extract feature. This module is called the Spatial Semantic Feature Aggregation module, to adaptively fuse high-level abstract semantic information and also low-level spatial features. Particularly in this work, we try to align the two modules, okay, because there are two modules, there are two issues when we do object detection. One issue is that we want to locate the object, which is the object localization, and then the other thing is class classification. We want to classify the object, is it what kind of objects? So that's why these two tasks usually may not align well. So that's why in this work, we also develop an IOU-aware confidence rectification module to help us to further improve the accuracy by means of aligning this. Okay. Further, we also formulate some distant variant IOU weighted NMS to try to improve the result by removing the redundant predictions, bounding box prediction. For details, please look at the paper. Okay, and then another follow work, which is a very recent one that we presented in CVPR just a few months ago, is that it is called the SE-SSD, in which our idea is to improve the performance without making a more complicated networks. Okay, our idea is to create something we call something people call a self-ensembled frameworks. So in this framework, we will take advantages of the soft and hard target. Soft targets means something easy. Okay, it means the original point cloud. So on the left hand side, and on the other hand, we can use some kind of data augmentation on the same input point cloud, and then produce some augmented inputs. Okay, for the networks. Especially here, you can see we have two networks. One is the teacher SSD, the teacher single stage detector, and then the other one is the student single stage detector. For the teacher's detector, we use the more easy more easy soft targets, and then for the student SSD, we use the more challenging hard targets. And then during this self-ensembling framework, we basically design some consistency laws to make sure the final prediction is consistent, even though those hard targets is created after some data augmentation. So by this means, we can enrich the teacher SSD, okay, by using the student SSD knowledge, okay. So the result, the good thing about this approach is that the teacher SSD actually has the same structure as the SSD, and both of them we have the same structure as the module, the feature extraction module that I present you in the previous work. So that's why using this approach without increasing the network complexity, we can improve the network parameter so that the network is able to produce even higher quality predictions than the previous work. Okay, and the good thing about this is very clear. So that's why it improved over the previous work we have. And then at the same time, because the network is a lot more complex than the previous one, we can also enjoy a very fast inference speed. And basically, you can say this kind of thing is based on knowledge distribution approaches. So that's why for detail, because of time, okay, for detail, you may also look at the paper. Okay, I guess I have to be faster. Okay, so let's move to another 3D understanding task, which is the 3D semantic segmentation. So what exactly is 3D semantic segmentation? It means that given a point cloud, we want to segment it into objects and also identify what kinds of object it is. For example, walls, chair, tables, a refrigerator, and so on and so forth. To do so, we have to design and train a deep neural network to predict a class label for each point in the 3D point cloud. A class label means the type of the object that the points belongs to. And in this work, our key idea is that we don't just predict a label for each point. We also predict a label for each edge. So what exactly is an edge? Actually, in this work, we try to connect points that are close to each other by an edge, and then we try to predict whether these 2 points have the same label, have the same class label. So by doing this, we can hierarchically create a graph over the structure and then try to produce something we call an edge loss, formulate a edge loss to try to encourage more information exchange in the graph, okay, to encourage the network to learn more results, to produce that results that is more consistent between the adjacent points. Okay, so let's go faster, I guess. Next, we will further work on another work, which is on 3D instant segmentation. 3D instant segmentation is more than 3D semantic segmentation, because for instant segmentation, we have to predict not only a class label for each point, but also an instant label or instant ID for each point in the input point cloud, which means that we have to further separate the objects into individual objects. So our key idea here is a point clustering process. Okay, we try to incorporate a point clustering process in the middle of an end-to-end network, which is trainable, and then we call this one a point group, as so here. And first, basically, after we extract per point features, we try to create, to predict 2 branches. One is the semantic branches to predict the semantic label for each point, and then for each point we also predict an offset, vector to try to move each point towards the centroid of the objects. So by doing so, we can create 2 point cloud. One is P. P means the original point cloud, and then the other one is Q. Q is created by shifting P, with the offset vector for each point. So that's why you can see in Q, the points are more concentrated near the object center. So by doing so, we can have 2 point set, which is the P and Q, and then we create another networks based on this P and Q to predict the object proposal or the clustering proposal using the scorelet. By doing so, we actually can take advantages of both P and Q, and then in order to produce a more accurate instant segmentation. So that's why from this result, you can see that by using both P and Q, we are able to create a better mean AP, mean FH precision than using P or Q alone. And furthermore, the good thing about doing so is that we also try this method, on both ScanNet V2 and also the SVDIS dataset. And PointGroup, this method actually can produce very good performance compared with the formal best solution in terms of mean AP, as so here. Then the next thing I want to introduce is label efficiency. So for 3D semantic segmentations, most work actually nowadays just use assume fully annotated point cloud data. In this work, we actually suggest that can we use both labeled point cloud and unlabeled point cloud simultaneously to train our segmentation network in such a way that it can learn from both labeled data as well as unlabeled data. Since I don't have enough time, I think I will skip the technical detail. I hope you roughly understand the main goal of this work. Another approach that we have tried to reduce or to the annotation burden or to try to make the label efficiency higher is that we try to allow us not to fully annotate the entire point cloud, but rather just to provide 1 point for each object in the point cloud, as so here. So here we show that this kind of work is that by using even just 1 point cloud, 1 point for each object, we are able to train using this self-training model to train the entire network in order to produce a result that is quite natural, by means of just a few iterations in this self-training process. So due to time limit, I guess I have to be even faster. The last word I want to put in more time because I think this word is quite interesting. Because in this work, we try to solve the problem that if we have point cloud data, can we use the point cloud data only during training to improve the 2D image segmentation network? Which means that can we train the 2D segmentation network, which is this 2D CNN I saw here, okay, to improve it to produce better 2D segmentation result. So the challenge here is that we can have 3D point cloud data only during the training process, but not during the testing process. So how can we achieve this? So our idea is that during the training, we try to train the 2D CNN networks to produce something we call the simulated 3D features. And then we use a consistency loss between these simulated 3D features and the 3D feature extracted from a pre-trained 3D segmentation network. So by doing so, the good thing is that if we can train the 2D networks to produce these kind of simulated features that are similar, okay, to the 3D features from the 3D CNN, then during the testing, we do not need point cloud data anymore. We can get rid of the top pass and only use the 2D CNN to produce these kind of simulated 3D features. And then during the testing, we can simply use these simulated 3D features to improve the performance of the 2D segmentation. And as so on the right result presented in this slide, we can see that our 3D to 2D distillation approach actually can improve the overall performance, okay, of our result. And we can actually improve the performance over other methods based on some generic knowledge distillation or some depth-based method. Okay, and finally, I think I have to go faster and then just quickly overview this kind of different kinds of downstream application that my group has done. Okay, here I want to show you some results on the following applications. The first two basically are related to geometry learning and 3D shape generation and manipulation. And the third one is on robotics. And then the last two are on some augmented reality. Okay, for the first word, I think the second talk we talk about it, so I will skip it, but just talk about the interesting part in this word. In this part, I think the most interesting word, the most interesting thing about this word is that we designed an unsupervised network, which means we don't need to have any label. Okay, we don't need to label where are the distinctive region, but our network can, based on some clustering method, it can detect and then find out what are the distinctive regions on different objects compared to other objects. As you can see in this result, we can highlight the engines on the aeroplane and also highlight different parts on the 3D shapes that distinguish it from other objects. And then in the second word, which is quite recent, in a few months ago, presented in SIGGRAPH 2021, in this word, we try to create a generated network, okay, to generate the network with some code. And then the interesting thing about this word is that we have a code that is attached to different points on these Pia objects, which is a sphere Pia. Then we, based on this information, something related to this entanglement, okay, we can allow some kinds of manipulation. Okay, for example, multi-strip parts manipulations or composition, and also part-wise interpolation and also strip interpolation. Okay, please stay tuned. I think in the third talk today, Roy Kwai will also present more detail in this work. And then in the third word, we actually try to practice our 3D sensing pipeline, okay, on different kinds of robotic scenario, for example, beam picking and also box gripping, as shown here. Okay. And using this method, we found that we can really enable the robot to locate, to segment out the point cloud as well as the image space for the objects. And then after that, we can also enable the robot's arm to more efficiently pick up individual objects as shown in these demonstration videos. Okay, and then the last two is related to AR. Okay, basically we have done two works on AR based on 3D sensing. The first one is that we try to sense where are the building plane and also where are the fall lines. Okay, and then based on building plane and fall line, we try to allow some AR content to be more effectively overlay on the building plane, which is fall level line aware or building plane aligned, so that we can produce this kind of AR applications. Okay, and then another word which is quite recent in ICCV 2021 is that we try to support and enrich direct hand interactions. Okay, and then in this word, the most interesting part I think is that we try to align the hand, okay, the real hand together with the virtual reconstructed 3D hand mesh, not just in the real space, but also in the finger level. So by doing so, we found that we can more accurately produce the hand meshes, and then this kind of hand meshes can be done in real time by our methods, generated in real time by our method, so that we can take it to enable this kind of direct hand interaction, as you can show here. Okay, which means that by doing so, based on our method, we can enable the user to use bare hand to directly grab and also manipulate different kinds of virtual objects. Okay, as you can see here in this video in an egocentric view. Okay, so I think time is short. Okay, I'm near the end of my part. Okay, and actually I guess I'm too ambitious to try to overview almost 20 papers already. Okay, so I hope you enjoy the talk, even though I do it very quick. Okay, but I didn't go apologize that I didn't go very deep into the technical detail. Okay, but still, when you see so many work that I have done, I really want to say that to make all these work happen, okay, I need the support, okay, from my research student and also the research staff. And I'm very grateful, okay, to have many talented research students and also postdoc in my team, as well as the student helpers and collaborators who helped me a lot in doing all this research work. Besides, I also would like to thank the various funding agency and research center for supporting my research work. Okay, I think this is the end of my part. Okay, let me unshare the screen and pass the time to Song Pang, okay, for introducing Sanji Lee, okay.